Hello, everyone. This is Eaton Donald, CEO of Trident Technologies. I am joined today by Mark Jewell, company founder, and today we're going to be showing an example of custom canvas for marine custom canvas fabricators. Here we are showing a cockpit cover or an example of a cockpit cover. This may be different depending on the type of boat that you're working on. And what we're going to be doing today is processing the patterns associated with this cockpit cover and showing you the workflow in ExactFlat using what we call 3D to 2D digital patterning. We're trying to create these patterns in an efficient manner that's going to be much more efficient than doing this manually. Mark, hello.
Hey, Eaton, how are you doing?
I'm well, thank you. So Mark, what I'd like you to do is I'd like you to show everybody what's involved in creating the patterns for this boat cover here, please.
Sure. So, Eaton, we have a good mesh, but one of the tools I'd like to show everyone is our remesher, our uniform remesher. We have a couple of different meshing techniques. One of them is called a uniform remesher, and what I'll do is I'll remesh this cover or top so we can take a look at what a remeshed surface would look like.
And so the mesh is important because it represents the fabric pieces itself. Is that correct?
Exactly. So basically, the better
mesh, you have a good representation of the parts that you're going to manufacture.
Exactly. You want to start off with a good mesh because, as they say, garbage in, garbage out. So good mesh is going to give us a really good pattern.
And so I'll just point out that we are showing ExactFlat for Rhinoceros 3D. This is a model that was captured through a digitizer in Rhinoceros and then brought into Rhinoceros 3D. Mark, why don't you show the remeshing process and then talk a little bit about what we do to get to flat patterns?
Sure. So the first thing I'm going to do, Eaton, is use a command in Rhino called weld vertices. And this is going to kind of take out any of the wrinkles or bad triangles in the surface. So I'll just highlight the part. And as you can see, all these points light up, and I'm just going to hit enter on the keyboard, and then I'm going to go into our first set of tools, our first tab. These are the ExactFlat tools, so the mesh tools. I'll click this, and I have a mesh validation tool, so I can basically select the surface again and hit enter, and up here it says all the meshes are valid, so we have a good valid surface to work with. Then I'm going to go to our next tool over here, which is our uniform remesher. And again, I'll highlight the piece and hit enter on the keyboard. And this is going to bring up our remeshing dialog box. So what I want to do is I'm going to hit sew and respect our seams. Then I'm going to have it unsew and delete the input. And deleting input means that basically once it's created our new mesh, it's going to get rid of this old mesh. If I don't click that off, I'm going to end up with two meshes, a good one and a bad one. The next thing I want to do is go into our smoothness. So the boundary, which is the boundary perimeter out here and around here, I'm going to set at 90. And I'm also going to set this one here at 90 for smoothness. And the vertex count is set at 300. So that would mean 300 faces or triangles. I'm going to bump this up to about 1800.
So that increased vertex density should lead to a higher accuracy mesh around curves. Is that correct?
Exactly.
All right.
And by the smoothness, that actually adds a little bit of smoothness around these curves. So I'll just start this off, and we'll see how the mesh is changing. So right now we're adding more vertices, and you can see visually how it's changing the mesh.
So it's reorienting the vertices, and it's adding more triangles to create a denser mesh. Let's talk a little bit about, before we go on, the reorienting of the vertices, because that's essentially one of the techniques that we use for flattening to get rid of strain and sag. Is that correct?
That's exactly it, yes.
Okay, so by changing the vertice, we are smoothing the material or relaxing the material, and we're also finding areas of sag where we want to put more tension in the material. Is that the...
That's exactly correct.
Okay.
So it's like fabric simulation.
Okay. So now that we've created a good mesh, which is the start of our process of creating digital fabric,
Mm-hmm.
where do we go from here?
So once we've created this nice mesh, the next thing what we'll do is go into our tool set. And our first icon here is basically the select pieces for flattening. So as you can see here, these pieces have already been assigned by the designer. So these are basically how the pieces are going to flatten.
So this is
And
a 3D model with the split lines already in place. The split lines represent pattern edge boundaries.
correct. So what we'll do here is we'll go in, we'll select our flattening tool, and again, rectangle, select the part, hit enter on our keyboard. And now you can see we have our 3D model here, and we also have our 2D pieces laying in the background. So what I'm going to do is just highlight or make this ExactFlat pattern active, and I'll turn off these other layers, and we'll go into our top view, and I'm going to zoom to extents. So we have all these pieces in, and I'll just turn this into wireframe so you can see when the flattener flattens the pieces, it actually assigns numbers. So it's like a paint by number, or you can line up the pieces. Now you have actually identification on each one of these pieces.
So this is just useful for keeping track of which piece is assigned to which piece, neighboring pieces, and if you have larger, more complex projects, then the numbering of the pattern pieces is helpful just for downstream processes.
Exactly. So I'm just going to go back into here, and we're going to turn on our finite element analysis, which actually shows the strain on the part. So I'll go into the shaded view here, and there isn't a lot of strain, but you can see here there's a like crimson color. This would be maybe 11% strain on the part, but we haven't optimized it yet. So this is just kind of give us a visual cue of where the stress and strain would be. Here's another good example here of a part that has a little bit of strain in it, but as I said, we haven't gone into flatten it or optimized it yet. I'll just go back out here, and now what we're going to do is go to our next tool, which is our optimize tool, or some people call it the spring tool, and we'll go in and we'll select the pieces that we want flattened. And I'll just hit enter again on the keyboard, and we'll watch what happens. So right here, we have our material settings. We can browse different materials that we may have. So I'm going to use a sunbrella type material, and I'll just hit OK here. And I'll hit OK on our material settings, and we'll see how this tool works. So it's going to go through each piece, and it's going to get a try to obtain a zero strain on each piece, or zero energy on each piece.
So if it's zero energy on each piece, that means it's eliminating both the strain and the sag. Is that correct?
Exactly. And that's how we get a very accurate pattern.
So from a geometric perspective, you are trying to maintain the seam edges adjacent to pattern pieces,
Mm-hmm.
while at the same time reorienting the surface area. And I can just see the surface area is changing on some of these pieces
Exactly.
in such a way that the strain and sag is eliminated.
Correct.
Okay.
So if I go over here, it's finished. So that took about 56 seconds. Again, that has a lot to do with how we redid the mesh. We made a really nice mesh, and next thing we.
Okay, so could you just arrange these pieces
Sure.
in a way which is visually similar to the way they're going to be sewn together?
Sure. So one of the unique features that we have in this tool is what we call our find feature, which is in our tools. And if you look at here, the binoculars, That kind of represents our fine tool. And I'm going to set our offset at about 10 inches. So we're working in imperial units. So I'm going to set this at 10 inches. And I'll just go around. And as I select an edge here, and you can see when I select an edge here, it'll actually pick the piece and highlight the piece that it gets matched to or mated to. And
so is this because the individual vertices in 3D are associated,
and
then you maintain those associations in 2D?
correct. So that's a very valuable feature. You know, in other 2D tools that are used for patterning, you would have to eyeball all these pieces because it's coming as a 2D piece. In our software, we start off in 3D, as you said, and we transfer the vertice information from the 3D model to the 2D piece. So we know exactly where everything fits.
So eventually these pieces are going to be sewn together. So this is not just a time saver in laying this pattern piece out visually. It's also a way to ensure that your pieces will fit together perfectly.
Okay.
People want to
Correct.
know about the accuracy because so many different programs out there are claiming to flatten from 3D to 2D, but they have problems with production level accuracy. So what I'd like you to do is I'd like you to go through a process of measuring pattern pieces in 3D, and we're going to compare them to the measurements in 2D.
Okay, so what I'll do here is I'll just go back into our layer and I'll turn on our mesh. So we have here over here our 3D piece, and over here we have our 2D piece. So I mean, you can see that this is in 3D. And I guess what we can do is we'll just start measuring. We'll start from the bottom, Eaton.
Okay, sure. Why don't we start from the bottom? So piece number 3, what is the 2D measurement and what is, or whichever you want to do first, the 3D or the 2D?
Okay, I'll start over here with the 2D.
Okay.
So I'll go to piece 3.
Yeah.
I'll highlight that, and we have a area of 704.866. And
Okay.
if I go to my 3D piece here and hit enter, we have a area of 704.065.
Okay. So we are off by about 3/4 of an inch, 3/4 of a square inch.
Right.
On 700. So that is, for production purposes, perfect.
Exactly.
Okay, let's go measure some of the other pieces, please.
Okay, so we'll do number 2 here.
Okay.
2D, so we have 2,821.97. And if I select piece number 2 in the 3D, we have 2,820.97.
Okay, so we're off by about 1 square inch on 2,800 square inches. Again, from a production standpoint, that's essentially perfect.
Right. So number 8 is 1918.39. And if we go into number 8 here, we're at 1917.51.
Okay, more or less a 1 square inch on almost 2,000 square inches.
Number 7, the small piece here, is 100.86. And if I go to number 7 here, whoops. And we're at 100.80.
Okay, and then let's get to number 9, because that was one of the pieces that had some strain in it and some sag points as well, if I remember correctly. If you can do both of those as well in 3D or in 2D and 3D, please.
Okay, we're at 2307.02 in the 2D. And and 2306.12.
Okay, that's off by about an inch, 1 square inch on 22,307 square inches. So from a production standpoint, that too would be perfect.
Right. And if we look at number 10, 562.14. And number 10 here in the 3D, we're at 561.49.
Okay, a little bit more than half an inch, half a square inch there. Again, perfect.
Okay, and this selection here, number 11, 451.68. And in the 3D, we have 451.32.
So if we look at all of the 7 pieces that we've measured combined, the area of the 2D parts are 8,866.92, the 3D 8,862.27, for a variance of 4.65 and a total accuracy of 99.94%. I think everybody would agree that this is well within the tolerances that would be considered acceptable for manufacturing. And the key point we're trying to make here is, in about 5 minutes, you get what are essentially perfect patterns. Okay, I think that's enough of checking the pieces.
Okay.
Let's talk a little bit about why it's so accurate.
Sure. So one of the main features is that we're allowed to select the material that we're flattening. So the yaw on the left of that material is now simulated in our flattener. So we basically get very, very accurate results because we're actually using the material that you would use when you're manufacturing.
Okay. So there is material assigned to the surfaces. What are some of the other reasons why it's so accurate?
The other reasons that it's accurate is the ability for the software, as I said, to simulate the pieces and also to check for the energy, the yaw on the left energy in the parts. So when you take the 2D and you wrap it back onto the 3D, you'll have no sag and no bunching up or wrinkles of the material.
Okay, so it's in part because of the way that we construct the mesh pieces in the beginning. It's in part because of the way that we assign the engineering characteristics of the material.
Yes.
And then it's in part in the way that we have the mathematical algorithms simulate the strain and the sag.
Correct.
Okay, let's talk about the things that you need to manufacture these things and put these pieces together so that they do fit. Show me how you notch, put alignment notches in here, and let's have a discussion about why those are so accurate.
Since we're, as we mentioned, we're going from a 3D to 2D, then we trap the vertices from the 3D and onto the 2D. When we add our notches, and I'll just add a eye notch, or some people call it a slit notch here. I'll hit my add button, and as I go around, you can see when I select one edge here, it knows exactly where this goes into all 3 pieces. So this notch gets sewn to this piece, and it also gets sewn to this piece. So this gives you a very accurate way of, as I said, we used to call it walking the pattern, where you have to eyeball. In this case, the software knows exactly where the notches go. Again, you can see.
So how does it know that? Let's just talk a little bit about that. Help people understand how it knows precisely where to put. If you select a location you'd like to have a notch, it finds the location on every adjacent or related pattern edge. How does it know that?
Well, here, I'll just throw this one more piece. Actually, maybe what I'll do is I'll zoom to extend so we can see the model. And as you can see, the notches on the model are on the 3D model. So because we know where the vertices are on the 3D model, when we go to the 2D model, it basically knows exactly where to place these notches. So for instance, if I go into this area here, there's a notch that would go right here. I'll place it right here. Now if we go on to our 2D pattern piece, you can see it's exactly notched where it had to be. So we can notch the 3D shape or the 2D shape. Whatever we do to the 3D happens to the 2D and vice versa.
Okay, so this is based on, the accuracy is based on the vertice locations.
Mm-hmm. Yes.
And because the pattern pieces are associated to one another in 3D, and the pattern edges or the seams are associated to one another in 3D, during the flattening process, those precise locations are maintained. And therefore, when you place a notch on one edge, you do not have to guess where it goes on the other edge.
Correct. Exactly. So it knows exactly where the notches have to go.
Okay, so we were talking about accuracy before. So accuracy really means, can I put together a sewn, fabricated piece of custom canvas for an individual boat and have it fit perfectly? Because that's what people care about. They just care that it fits perfectly and it's correct.
Right.
So there is the meshing process at the beginning, which is the start of the creation of what we call digital fabric. Then there is the highly advanced mathematical algorithms, material assignments, and so on. That is part of the flattening process.
Right.
And then we have here the notch locations for the sewers so that this can be put together in an accurate way that leads to great fit.
Correct.
Okay. Why don't we put a few more notches on? Just zoom out if you wouldn't mind. Just show people how quick and easy it is to do this. And then what's the next step after that? So just go ahead and put some notches on if you can walk us through the final steps of the process.
Yeah, so basically I'll just add some notches here and here. I'll put a notch here and we'll just quickly go through and you can see how quick this works. You can imagine what it would be like if you had to use your eyeballs to eyeball exactly where all these notches went. It would drive you crazy. So I'll just go through here. And let me just zoom out here a bit and I'll put one here. So you can see we've got basically all the notches added onto the piece or ready to go. I'll just get out of my notching tool, close that. Next thing we'd want to do is export the DXF. So we don't use the Rhino export DXF, we use our own export DXF, and the reason being is all these notches and all that information, if I just saved it out as a Rhino DXF, all that information would be lost. When I save it out as a ExactFlat DXF, notches, seams, all that information is going to go out to the DXF for our cutter or our plotter. Another thing I'll just show real quick, Eaton, is if I go into our tools, and we're in our ExactFlat tools, and I go to my DXF export, you can see that the seam line set at 1/2 inch, and my notches were 1/2 inch as well. So this is a very large canopy or cockpit cover. So when we go in, we can take a look at how that's going to look in our DXF. I'll just export out the DXF now, and we'll just call this cover. And I'm putting it on my desktop. So we'll go here. We'll open up that file. Go into DXF. And we'll select cover. And we're in inches. I'll just hit OK here. And there you can see our cockpit cover. And if I zoom in, you can see all the notch locations that I put. Notches here. And the notches up on the top here. If I zoom right in, you can see this green, it's a green notch. These all show up in our layers. The N just represents N for notch. You can have any number or letter. So basically notches would go A, B, C, D, E, F, G, or 1, 2, 3, 4, 5, 6, 7. That can all be assigned in the ExactFlat tools. So if I just zoom out here, as I said, we can turn on or off our grain line. The grain line is just giving the direction, the grain direction. That's this white line in here. Just shows the direction of the material. Our cut line here can be turned on or off. Our notches, which are green, you can't really see them, but they can be turned off and on. Our seam lines can be turned off and on. And our notch tags, which would be the N, can be turned off and on. So there's quite a bit of capability for the software. As I said, these layers would be exported out to a plotter and a cutter. The XF files can be easily read by any of these systems, any of this hardware. So this is.
And if you wanted to do further finishing of the 2D patterns, you could import this into your preferred 2D patterning tool of choice. Okay. All right. I think we'll wrap it up there. The process, were you to run it without my interruptions, appears to take about, in this particular case, maybe 5 minutes.
Yes.
Okay. Well, Mark, this has been very helpful. Thank you very much. We will stop it there. I hope people find this information useful and first and foremost educational. If you want to know more, please contact us, www.exactflat.com. Mark, thanks for your time, and I will talk to you again.
Thanks, Eden. Good night.
Good night.